for the application of functions to real-world behaviors of various things in the real world, many of which we'll try to get a good look at once we get this basis down. For many, many applications, one of two big deal numbers governs our mathematical model. One of the big deal numbers is this number here, the y factor of the original graph that causes a slope graph of zero concavity. We're going to try to find that value. Okay, so what is that y factor? Now, we can get a pretty good idea of what that y factor might be by constructing graphs and constructing slope graphs, in the process getting an even deeper understanding of power functions. We can't prove anything, don't think we can prove anything geometrically, but actually maybe we can, because I haven't really tried to prove this geometrically. Because at this point, an algebraic proof turns out to be easier. Now we'll see what that means. Right now, the task is the search for this number. Can we narrow this number down? Can we have some number that we know is a negative gives a negative concavity and some y factor that gives a positive concavity, with those two y factors not being far apart? Now we know if we construct these graphs that y factor 5/2 gives us a slope graph that's concave down, y factor 6 gives us a slope graph that's concave up. So if this number exists, it's between 5/2 and 6. That, in decimal, that's between 2.5 and 6. Well, that doesn't narrow it down a whole lot. Could we narrow it down much closer? Let's say that the number was 4.78. Could we narrow it down to say, well, it's between 4.5 and 5? Okay, I think we can narrow it down. It's between 4.6 and 4.9. Okay, can we narrow it down? How well can we narrow it down? With some confidence. How well can we construct our graphs to let us confidently predict at least a narrow range within which this number has to occur? Then for an exponential graph, what we're looking for. Okay, here's a representation of an exponential graph. I don't know if it's a very good one. It's got kind of the right shape. In this graph, I'm actually going to put a scale on it. The graph is 0. Graph goes through the point 0, 1. Well, any basic exponential graph, y equals b to the x, any number to the 0 power is 1, so it's a no-brainer that that graph would go through the point 0, 1. Now, we want to know a doubling displacement such that the slope of the graph at this point is 1. Now, if we change the doubling displacement, that is going to change the slope of the graph at this point. So we can manipulate the doubling displacement. We can make it bigger, we can make it smaller. We can manipulate it until we get a slope that's close to 1 and determine what the doubling displacement might be for that graph, so that we can find the value of b that goes with this characteristic. This is a huge big deal number. It's even a much bigger deal number than this one, but this is a big deal number in its own right. This is maybe the most fundamental number in mathematics. This is a very good and very interesting number, but not nearly as applicable to broad fields of mathematics as this number. So this is a great big deal. This is a big deal number. This is a great big deal number. So we're going to go out looking for it.